So let's try a Newton's law problem that's a little bit trickier, and hopefully you've already tried this yourself. If you have not tried this yourself, please make an effort to at least get it started or write down, draw the picture, write down maybe what you know and don't know. This is all meant to be practice. Remember, you can watch thousands of hours of football, but it's never going to make you a great quarterback. You always, always, always have to practice. So don't just watch me do the physics yourself. All right, so this one we want to find the acceleration for a box that's sliding down an incline, but eventually comes to rest due to friction. And once again, we're using Newton's second law, which is net force equals mass times acceleration, where force and acceleration are both vectors. And that's important because we're going to need to create vectors, we'll have force vectors, but we're also going to need to remember back to kinematics for this one. So we're going to start by drawing our incline, which I'll just draw a right triangle because that's the easiest way to think about this. And then we'll put our box on the incline. And then I'm going to make the box, a nice light color. Okay, so this box is going to be sliding up and down. So it's going to start up here. It's going to be sliding pretty fast, and then it's going to come to a slow stop down here. So we're thinking about it somewhere in between. What this tells us, looking back from kinematics, is we have some initial velocity up here, and then down here, our velocity final should be equal to 0, which definitely feels like a kinematics issue. The velocity at this point is going this way, but because it's slowing down, we know the acceleration has to be going this way. And you'll notice the path of the box is going to be parallel to the surface of the ramp. And the ramp is going to have some angles, so it has a right angle over here and then an angle over here. And that's going to end up being important because we're going to have to do some fun trig to make sure that we get all of our coordinates lined up so we can add our vectors, okay? So once again, we're going to just skip ahead to drawing all of our vectors on this point in the middle of our box, because then we basically have a free body diagram that we don't have to draw twice. There's a couple easy ones. One is the weight, mg, that's pretty straightforward. A little bit trickier is the normal force. Remember, the normal force has to be perpendicular to the surface contact. So here's our normal force. And last but not least, because we know the acceleration points this way, that means we have to have an equivalent force pointing that way. And that force in this case is going to be friction. And in this case, that's going to be kinetic friction, because we know this thing is moving, so it has to be kinetic. So here's our three forces, and that's great, but adding them is going to be a pain. So we need to determine what x and y are, and I like to use a technique for choosing my coordinate system where I start with the direction of the acceleration. And since the acceleration is parallel to this ramp, I'm going to draw my x and y to also be parallel and perpendicular to my ramp. And it seems I've drawn my normal vector a little bit funky, so I'm gonna redraw that so it's nice and on the line, because now we know what perpendicular looks like. Okay, so the nice thing about drawing our axes this way, so we'll call this y, and we can call this x, is that we only have to really fix this vector. This is the only one that doesn't line up with our coordinate system. So because we only have to fix that vector, we now just have to figure out what angle theta is similar to this angle theta, okay? And so looking at basically similar triangles, we can say, okay, this triangle, right, if we draw down from here, oops, say this triangle, okay, maybe I'll make it blue. This triangle, right, is going to be the same as this triangle, which is how we're going to figure out mg. Because these are similar triangles, and if this doesn't make a lot of sense to you, you can go back to thinking about, do some trig review, which we have in Canvas. But because these are similar triangles, this angle is theta as well. So what that means is we can create, and I'm going to use a slightly different color just so it's not confusing. Let's use pink. Component vectors that lie along this. So basically, we can break this mg into this vector and this vector, which can also be written over here, because remember, we can move vectors anywhere we want, okay? So this will be, because this one is adjacent to your angle theta, that's going to be mg cosine theta. And the one over here, since it would be the one over here on the triangle, is going to be mg sine theta. And now we've basically gotten rid of this vector and broken it into two different vectors. So that brings us back to, now that we've drawn our picture, we have all of our different little vectors lined up along our coordinate system, we can actually go back to our Newton's second law, and we can sum up our forces in the x and y direction. So in the x direction, right, we have, in the positive direction, we have mg sine theta, and then we subtract the kinetic friction, and that's going to be equal to mass times actually a negative acceleration, because you can see acceleration points in the negative x direction. For the y direction, we have n in the positive direction minus mg, which is the weight. And of course, we have no acceleration in the y direction, so this becomes ma y, but of course, that's going to give us 0 because there's no acceleration. So we know that n is equal to mg, and that's going to be useful later because we know that mg sine theta minus friction, and friction, okay, remember kinetic friction is equal to mu kn, so we can write this as mu kn, and then this is equal to minus ma. Now it's really important that you remember the sign here, because your coordinate system is set up in such a way that your acceleration has to be negative, the way that we've done this. Okay, so since we're solving for acceleration, we now have these two equations to work with, and one of them is a lot simpler than the other. So we'll say mg sine theta minus mu k mg is equal to negative ma. Fascinatingly, all of our m's are going to cancel, so that means we don't actually need that, and then we're pretty much done. So acceleration is going to be equal to mu kg minus g sine theta. We've just done a little bit of algebra, and you can really rewrite this as g mu k minus sine theta. And so that would be your acceleration. If you need it to be a vector, you could call that the negative x direction or up the ramp or whatever. And that will give you a full picture as a vector version of acceleration. All right. The other thing we want to check is, does this make sense? And it should be less than g. So we're hoping mu k, we know mu k is usually less than 1, sine is less than 1. Hopefully this doesn't give us a negative because we haven't been given any numbers, but it looks like both mu k and sine are going to be smaller than 1, so g, it will be a fraction of g. Because remember, the fastest acceleration you can have is free fall if gravity is what's driving it. And so if we have something less than free fall, then we're going to have an acceleration that's less than g.